Move on to machining operations and machining tools. We're going to discuss turning and related operations. Then I'll go into drilling and related operations. Then I'll go to milling. Machining is a material removal process in which you use a sharp cutting tool, and that is used to mechanically cut away so that the desired part geometry will remain. So you're just taking material away. Most common application you'll see these metal parts, and they tend to be the most versatile of any manufacturing techniques that we'll be discussing because you can produce a variety of shapes, geometry features with high precision and accuracy. You can also use casting, but we'll talk about it later. Casting can produce defects and is not as accurate as machining. With machining, you can achieve very high level accuracy. So you have classifications of machine parts, and then first we'll look at the cylindrical or disc-like shape, like the left here is a rotational kind where you have a rotating part, and then you have a non-rotational part like a block-like or plate-like, where you're not rotating a piece, but you're machining in other ways. So each machining operation produces a distinctive characteristic part geometry due to two factors. You have the relative motion between the tool and the work part. Again, the work part is the one that you're working on to produce the final product. And then you have, in the case of the relative motion between the tool, which is depicted in gray, and the work part, we'll first talk about generating. So the generating approach, it uses a relative motion between the tool and the work part. In the part geometry, this part here, its geometry is determined by trajectory of the cutting tool. So this tool is rotating, and how, depending upon how this traverses or how these, what is the trajectory of this tool, you'll generate a shape, and that's what's called a generated surface. Two, the shape of the cutting tool. You have a forming, so you have a formed surface here. The part geometry is created by the shape of the cutting tool, and in this case, you can see here that the part is being rotated, and you have the tool here that is in place. And as this part is being rotating, it forms that surface. So the part geometry is created by the shape of the cutting tool itself. While with the generating approach, the cutting tool is moving through a trajectory that shapes the work part. Again, two factors that determine the part geometry. Now let's look at the generating shape, which is the first kind that we discussed, and then there's five of them that we can talk about. And they're all talking about the same thing where you're removing material, the part is moving, sorry, the tool is moving relative to the work part, cut, and then the shape is being generated. So the first one here, A, called straight turning. You have a force applied, and this is moving towards the left. You have a velocity being applied here, rotational, and as the work part is being rotated, it generates a cylinder. And as I continue to apply that force, I will continue to remove material towards the left. B, you have taper turning. In this case, the generated surface is a cone because this trajectory is such that it's moving at an angle while the part is rotating, thus causing a conical shape, which we call taper turning. C is called contour turning because the trajectory of the tooling takes a particular trajectory as the part is getting rotated. And that causes a generated surface that may not be a cone or cylinder, but C is a more generic version of A and B. And then you have plane milling, which is here again, you have the work part here. Now, in this case, the tool is being rotated. And again, here in the top one, A, B, and C, the work part is being rotated while the tooling here following a trajectory that with the rotation is causing that generated surface. Well, at the bottom, what you see here is the tool is the one rotating and is removing material from the work part. And you can see here that we call this plane milling. And then E, you have profile milling, which is the one I had shown earlier, where you have this tool that's rotating and then it's taking a trajectory that allows it to create the generated surface on the work part. So forming to create the shape. So you have three ways to do this. A is, and now I'm going to this bottom one here, right? Forming. So I covered the one on the top, generating surfaces. The bottom one is forming. So for that one, you can have a form tool that pushes up as the work part is being rotated, and that causes the form surface to occur. Then you have drilling is a perfect example of things you have actually done, which is here you have this tool that pushes downwards, is rotating, and in this case, a form surface is created. And you can see that's forming the part. And then here's another example called broaching, which is you have this tool, there's a part, and this is going through the part, causing this work part to have that shape. The combination of forming and generated to create shape, you can take forming and generating and combine them, and that will be done. For example, in the example here is thread cutting on a lathe and slot milling. So here you can see milling and thread cutting on a lathe. So turning is a single point cutting tool that removes material from a rotating workpiece to generate a cylindrical shape. And I showed that earlier. That work is performed on a machining tool called lathe. There's various turning performing operations you can do in a lathe. Facing, counter turning, chamfering, cutoff, and threading. You can do all that in that machine tool. And here's an example of an engine lathe. I'll give an example at the end with a video. Here's a diagram of an engine lathe showing its principal components and motions. You have speed controls here, you have feed controls, the headstock is here, you have the spindle here that allows the rotations, you have the feed, the tool post, the tailstock, the bed. So this is the foundation, the cross slide, the carriage, ways, and the lead screw. All these components are part of the engine lathe. You'll have experience through the lab portion of this course to learn how to use the engine lathe. And I'll show a video a little bit later that describes some of this. So when I look at the turning operations, you have the work part, that's your original surface, has an initial diameter, right? And as the single point tool that you have here, as the work part rotates with the velocity v that you see here, you can see here that you're chipping away from the material. So it's cutting away from the material. In more detail, we can see that here. And it's removing a amount d to get a final diameter d. That's what we call the new surface. The operations related to turning are the three that we discussed already, but there's three of them facing here, the taper turning, which is for conical type, and then the counter turning. They all have the same mechanism as this one here, but depending upon what we're doing, it is going to create, it's called differently. And then you have the form turning, chamfering, which I don't think I discussed, but it allows for chamfers to be created, and then cutoff that allows for a little groove to be created. And then you have other operations that allow you, by turning, you can then create threading as well, because you have this tool that has a shape and that chips away material to create these threads. You also can use boring to be able to create a bore, and then drilling, which can also create a hole. So there's various methods in industry of holding workpiece, holding the work between centers, chuck, collet, and faceplate. So here you can see the dot plate here, and that's going to allow you to clamp the work part, and that's driven by this work plate here. This is your work part, and then you have the center at the headstock end. And this is your work part you're working on. Here's a more visual view of that. Instead of this cartoon, you can see here in 3D what is going on. Here's your workpiece, the lathe dog, the drive plate, and the centering. So the methods of holding workpiece required holding the work between centers. You have to somehow hold it. You have the chuck that is here on B. So you have these jaws that have an adjustable clamp work. So you can see here the clamps here, and that's your work part. Then you have C, the collet, and the collet with three slits will permit squeezing of that work plate or work part. In this case, it's a bar, right? And that allows you also to then advance forward to squeeze forward or backwards. So by pushing this forward, the sleeve here, it then compresses into the material, allowing it to be held in place for then do operations. The final one is the faceplate, where you have this faceplate here that's attached to the spindle. Here's your turning the work part, and then here's your clamps that bring this work part into place and hold it into place. So again, for approaches, holding the work between centers. So there's one center and there's the other side, the chuck, and then the collet, and then the faceplate. And they all work very similarly. They're all trying to hold the part in place. Here's a CNC turning center. It's an industrial robot to load and unload parts. Drilling, it creates a round hole in a work part. So you have your speed motion here, that tool, that's your drill bit, and as you push forward, that's your feed motion. Then you create the hole in the work part. This needs to be compared to boring, which can only enlarge an existing hole. So that's the difference there. Cutting tool called a drill or drill bit, and then machine tool, which is called a drill press. And so the drill press is an upright drill press and stands on the floor. The bench drill is similar but smaller and mounted on a table or bench. Here you have the head power, the column, the base, the table, the spindle, and the adjustable head. And here's where you will have the drill bit, and they'll go into the part. We call this a drill press. Now there's two types of hole. One is called the through hole. The drill will exit the opposite side. And then you have the blind hole where the drill does not exit the opposite side. These drill bits typically will have an angle. We call this the point angle theta. Will have a diameter, and then this is your work thickness here, T. You also have, in this case, a hole depth D. In one case, you know what's going on exactly. That's what's called a through hole. The other case, you is a blind hole. You don't know, but you have to use the tooling movement to understand what thickness remains. Milling is a machining operation in which work is fed past a rotating tool with multiple cutting edges. The axis of tool rotation is perpendicular to the feed. Cutting tool called a milling cutter here. The cutting edges are called teeth. The machine tool called a milling machine. And then you also have basic milling operations that create the planar surfaces. Other geometries are possible. You can also interrupt the cutting operations using this milling approach. There's two forms of milling: peripheral milling and face milling. So in this case, the speed motion of the tooling, the cutter in this case, that's your work part, and this work part is being fed into this tooling. So this speed motion is causing the milling, and that's usually in a cutter axis, and the cutting edges are on the outside periphery of the cutter. You then have the cutter axis in this case. Here is parallel, right? Here is perpendicular to the surface being milled. So the rotation and the feed are perpendicular. Here they're parallel to the feed. And in this case, we call this face milling for this scenario. And this is your depth that you're cutting through. That's your cutter. That's the rotation of that tool, the feed, and the work part. There's various types of peripheral milling. You have the work part here, sorry, the work part, and that's your axis of rotation of that tooling. Here's B is called slotting because I'm creating a little slot. While here in A, I'm removing part uniformly across. C is side milling. D is straddle milling because I'm creating a shape here. And then E, form milling because that tooling has a shape that when rotated causes a shape. There's other types of face milling. Conventional face milling, in this case, is removing material as you see here. And then you have partial face milling, which is only removing part, but again, this is perpendicular. The axis is perpendicular to the work part surface that's been milled. C, end milling. Here you can see another situation of part being removed. And then here you can see profile milling. That's going to cause a shape to occur. That again is face milling, is perpendicular to the surface of the work part. Pocket milling, very common in creating orthogrids and isogrids in tanks for launch vehicles, for example. Here, the tool is perpendicular, the axis is perpendicular to the surface being worked on, and we're removing material this way. And then here you have surface contouring again, perpendicular to the surface, and that's why it's called face milling. And here the tool takes a path that creates a surface contouring. The machining center is highly automated machine tool that can perform a lot of the operations we talked about under a CNC control in one setup with very minimal human attention. You'll code up everything up, you'll apply that code to the machine, and the machine will take over and apply those operations, milling and drilling, with three, four, or five axes that allow so much range of motion that allows you to create virtually any shape you need. Other features is automatic tool changing and automatic work part positioning. Pilot shuttles as well. I'll now show a video of some of these operations. I hope you enjoy this and I hope you learn something new.
Let's watch the following video.
The two-axis single turret CNC lathe is the simplest CNC turning machine. All tools are in a single turret, which is on a slide moving in two directions. Hence, it is designated a two-axis lathe. One cutting operation is performed at a time. Turn mill NC turning machines add milling operations to the machine's capability. For milling operations, the workpiece is held fixed or else rotated at a very slow speed while rotating tools, sometimes called live tools, are brought to it. The main benefit of the turn mill lathe is that more complex workpieces can be finished on the lathe and not have to be moved to a second machine tool for additional operations. The sub-spindle CNC lathe uses a secondary or sub-spindle to pick up the work from the main spindle. Another workpiece is then fed to the first spindle, running both spindles at the same time. Automatic screw machines are for high production turning and operate unattended. Cuts on the end of the work are combined with cuts from the side for rapid production. There are single spindle and multi-spindle types. The multi-spindle automatic is the premier high production turning machine. It can machine multiple parts simultaneously with multiple spindles. The 6 or 8 spindles are held in a rotating spindle drum. This drum rotates the spindles to the cutting tools positioned on slides. The CNC Swiss-type automatic is primarily for parts that are long and thin. To generate external features, the bar stock is fed longitudinally by a sliding headstock through a bushing past the radially arranged turning tools. Long, thin parts can be turned without deflection, as all turning is done adjacent to the bushing, which supports the rotating bar. Vertical turret lathes, or VTLs, are commonly used for large diameter round parts, not suitable for holding in the chuck of a horizontal lathe. The work is clamped on a rotating table 2 to 6 feet in diameter. Tools in tool blocks or turrets may be fed from above or from the side into the rotating work. Turrets, by far the most common tool-holding arrangement on production lathes, can hold from 6 to 14 tools and quickly rotate on command to bring the next tool into position. Turrets accept tool holders, which in turn carry the cutting tools. Work is held at both ends between centers, which are pointed conical pins or held at one end by a chuck, a collet, or if an unusual shape, by a fixture. Chucks fit on the spindle nose of the lathe and hold short, large diameter work. There are many types of chucks, and they are either manually or power operated. 3-jaw universal chucks are the most common. All 3 jaws move in tandem to grab a round workpiece, center it, and grip it. Irregularly shaped workpieces may be held in 4-jaw chucks, in which the jaws adjust independently. Collets, which usually seat in the spindle of the lathe, are hollow cylindrical devices with slots along most of their length. A collet opens under its own spring tension and is closed securely to grip the stock. They hold small diameter round work on center. Chucks and collets come in many types to suit various workpieces. Taper turning produces a taper along the axis of the workpiece. Tapers can be produced by offsetting the tailstock from center line or by using a taper attachment. Short, steep tapers can be turned using the compound rest. Facing squares up the end of a workpiece. It also finishes the work, or a single diameter to the desired length. Reaming enlarges and finishes a previously drilled hole by removing a small amount of material with a rotating fluted tool of the desired hole diameter. Boring enlarges and finishes a hole with a single point cutting tool, like a turning tool. The boring bar moves along the axis of the part, as in turning, but inside the drilled hole. Parting off or cutting off is like grooving, but with the narrow tool advancing to center, causing the finished part to fall off.
Now let's watch a cutting operation.